It'd be
Thank
difference
you.
calculus. The title's wrong, right? It's the difference calculus.
Ah, yes. Sorry.
I mean, that's sort of important. I have George
Yes, that's
Bull's
the whole
book
point.
there, which
Yes.
on the first page is discussing this
Indeed,
distinction. It's the main point of his book, written in 1860 or before. Maybe.
Indeed.
Yeah.
Yes. So thank you, Dennis, for inviting me to talk. And as said, paper that we wrote jointly with Dennis and Nissim. Okay, so the main idea is the idea of discretization is one wants to start from a PDE and to sorry, let me just get this going. Yes, wants to start with a PDE and discuss it. So in this example, put the sorry, it's not working. Okay, so I just written down a usual form for Navier-Stokes incompressible fluid, just as an example. So as a PDE, we have some functions, usually of time and space, and we have differential operators, time and space. Discretization that we're talking about will be discretization in space. So in other words, we want and have ODE evolution in time of functions on lattice points. So the time derivative will stay as a time derivative, and the spatial derivative one classically approximates by a divided difference. So one could use the standard divided difference, one could use a symmetrized divided difference. And we'll see that that's actually what we're going to be using in a moment. And then one classically ends up with some sort of ordinary differential equation, which you can run and hope that the solutions, when you refine the grid, will get closer and closer to the solution, the formative solution of the original equation. Okay, so one big problem with this is that there may be different forms of the continuous equation which are equivalent in their continuum form, which discretize to inequivalent systems. They may behave very differently, apart from being not exactly the same. They may even have different behavior for when h goes to 0. So the reason for this is that vector calculus identities, which one uses to show equivalent of continuum equations, do not hold in their discretized form. So for example, with Navier-Stokes, I just wrote down two standard forms, the convective form and the conservative form. And the equivalence is dependent on a certain vector identity, which doesn't hold. So in this case, we would have derivative of product being you differentiate one or you differentiate the other. And because in here we have the divergence being 0, so that is the equivalence of the two forms. So this sort of an identity doesn't hold in discretized form, and that is the crux of the difference between the discretized model. Okay, so the fundamental problem is Leibniz in the one-dimensional setting. So as we said, that the derivative of a product is not given by the usual form. So what do you have instead? So if we use the divided difference that I wrote up here, then we don't find that the divided difference of the product is given by precisely what we've written here. What do we have? Well, you can correct it. So there are many different ways of correcting it. The first way you can correct it is, say, by putting here g of x plus h And then you find that this actually works. So algebraically, this is now correct. Or no particular reason to shift the G instead of the F, so you could do the same. Leave G exactly the same, and here change the F. And that will also be valid. And the third thing you can do, well, you could leave this as G, and you could put here F, but now this is not correct because it would have been correct if I'd written F of X plus H. So now I have to add another term, which will be F of X plus H minus F of X times G of X plus H minus G of X over H. Okay, so I'll put over H here and write times H here. So now we have three different variations. So what are these three different variations? You could write them in shorthand by saying here we have the discretized version of the derivative of the product in the first case here is given by the discretized derivative of F times, well, it's not G, but the shifted G. We have G at X plus H here. So you would have a shifted G plus F times discretized derivative of G. So that's one way. You have the other way, shifting F instead of shifting G. And the third way is to say you have F derivative of F times G plus F times the discretized derivative of G. And now we have an error term. And the error term you see is H, in this case, times the derivative of F times the derivative of G, discretized, of course. So these, well, this is not the actual situation. It is a formalized situation, one-dimensional, and by using a discretized derivative, which is a one-sided divided difference. But this gives you an idea of three different ways in which you can try and correct the fact that the discretized derivative does not satisfy Leibniz. Okay, so now if we go to the continuous picture, if you look at differential forms on a manifold, then you expect them to form a differential graded algebra. So you have the algebra of differential forms, you have some sort of wedge product, and you have the exterior D on these forms. So that would take in all the basic objects that you have in classical differential equations, grad, div, curl, Laplacian, and so on. They can all be nicely put in that framework.
Plus the metric.
Wedge, sorry?
Plus
the
the
metric.
metric.
Yes, that's true. Yes, okay, you're right.
Plus the star operators. Yeah.
Yes. So classically, if you just deal with differential forms, then you have commutativity, well, graded commutativity, you have associativity, and you also have Leibniz. So you have all three properties in the continuous world, but it's a theorem, I think Dennis, many years ago, that there's no finite dimensional model on cells which preserves homology and such that all three properties are satisfied. So you have to drop at least one of these three properties. Okay, so, well, just to give an illustration as to what happens and what the possibilities are, let's say we subdivide into cells. So once you do that, you have chains and the boundary operator. So the boundary is going to be degree -1 with square 0, of course. And similarly, you can look at cochains, and there you have a co-boundary operator, which will have degree +1 and also square 0. And these are a dual in this sense. Adjoint, I should say. So now one can try and talk about multiplication. So for example, if we just look at cochains, so 0 cochains would be functions on vertices, 1 cochains would be functions on edges. Multiplying 0 cochains is not a problem because they are localized at points. So you would just take the value at a point to be the product of the values. What would you like the value on a 1 cochain? You could take f of A times G of E, or you could take F of B times G of E.
I think we lost a sentence or two.
Oh, you don't hear the sound?
Can you start with the top blue line in the multiplication? Well,
Sure.
you just said that, and then we didn't hear the rest. Yeah.
Oh, okay. Yes, sure. So I said that, yes, so I said if you're multiplying zero cochains, then there's no problem. They're localized at the point, and you can just multiply, take their product at that point. If you try and multiply a zero cochain F by a one cochain G, you want to get a one cochain. So now the question is, what are you going to associate with an edge, or one cell? So F times G on E, well, you have a choice. You could take, F is defined on points, so you could take F at A times G of E, or you could take F at B times G of E. So there is a solution to this, which which is the Alexander-Whitney cup product. So that defines a product on cochains. And then at points, this is what you would have. And for example, you could take this choice for, so you're matching the end of the first with the beginning of the second, so to speak. And this would be the cup product on evaluated on an edge. And this will then satisfy Leibniz. The problem is that it isn't symmetric. So there's a very particular choice here. So it's not commutative, it is associative, it isn't commutative. So the problem is...
But it is associative.
What you would say is...
What did you say about the properties?
Yes. So I said that it is, okay, see, down here. It's associative, it's Leibniz, we've just written that here, but it's not commutative.
Okay, good.
Not commutative because we have FA times, yes, and we've chosen a very particular sum here. So this is really geometrically, you can see that as the problem of finding a cellular approximation to the diagonal. What we have in this formula here is using, say, this cellular approximation to the diagonal, but you could equally well use the other one, and then you would get something else. So that would just be essentially taking the product in the opposite order. So here you would have F, G of E. We're using what we used up here, F of A, G of E, plus F of E, G. You could do it in the opposite order, which would mean you'd be doing F of E, G of A, plus F of B, G of E. So that would be going around the opposite direction. Yes?
Your the second line there, the F cup G evaluated, yes, confuses me because F is a zero cochain and G is a one cochain, and on the right you're evaluating.
Yes, you're right. So here F was a zero cochain and G was a one cochain. But then when I moved down to write the formula for Alexander-Whitney cup product, they were just arbitrary cochains. So you just take arbitrary maybe some combination, not homogeneous, yes? And then you can ask what will give, so at a point, you take just the evaluations on the points, okay? For this, which piece, what will you get on an edge? Well, you'll get this is the zero cochain part of it, and this is the one cochain part of it. Okay, so you've got those pieces. You've got a mixed cochain here. It's okay?
Well, but when you evaluate the zero cochain on the one chain or the one cochain on the zero chain, are those automatically zero?
It will zero.
Okay,
yes.
Great.
Exactly. Yeah. Okay. Yes, so we could do exactly the opposite. So in other words, effectively G times F, but we're calling it F times G, and that's the formula we have here. And that, of course, is still associative, and it still satisfies Leibniz, and it's still not commutative, but it's different. So remember that satisfying Leibniz is this quantity here. This is really saying that in some sense, D and delta, I should say, and your multiplication commute. So now we're saying, well, if you just turned it around, it would still commute. And so you could take the average. You could now take the average. And if you took the average, then it would be commutative, because that's what you've done. And since the relation for being Leibniz is a linear relation, then in delta, then similarly, it will still obey Leibniz, but now you've lost associativity.
Although some mathematicians have missed this point and actually written preprints.
I see.
And one did when I was a graduate student who won't be named.
So you can pursue this, and it's a very interesting story. If you use this model, then you get to differential graded Lie algebras and C infinity structures. And if you use this model, you can go to associative infinity algebras and get some interesting story too. But neither of these is the one we want to pursue. So what we want is something which is both commutative and associative, and therefore we're going to have to drop Leibniz. So we take the third route. And the way we do that is to localize cells at their centers. So in order to do that, we have a center, which is actually part of the geometry. And so we think of cubical cells as localized at their centers, and we multiply pointwise. So then I'll write down exactly what that means in a moment, but then we'll have an obviously commutative and associative multiplication, but it won't satisfy Leibniz. Geometry we want to take us with a lattice spacing of H, and the whole size of the lattice will be, say, 2n by 2n by 2n. So if you like, you can think of this as, say, n being something very large, some power of 2, H being something very small. So I do this, and we have a unit cube that we're subdividing in each direction to the n+1 pieces. And so this is what we would want if we want to discuss periodic boundary conditions. And so the geometry is really just that of the 3 torus. Okay, so now what we do is we consider chains to be generated by elemental cubes which are of double size. So all the elemental cubes that we consider will have edge length 2h. And the reason for that is that then they will have a center which is also in the lattice. So the space of chains will be labeled by, well,
could you
so
draw two that overlap just to make sure that not assuming it?
Sure. So we could have one like this. This is a two cell, and there's another 2 cell.
So you have all those.
Yes.
Yeah, right.
Yes.
Yeah.
Okay, so the type, yes, so the chains are generated by elemental cubes of all dimensions, 0, 1, 2, and the so an elemental cube will be determined, use this notation IA. So I is the type, so that says in what orientation it is, and A is the center. So that will specify. So for example, what I've got here, this would be your A, and this would be, say, XZ. So this thing you could label as XZ at the point A, where A is this point here.
I don't understand.
So this is the chain.
I don't understand the notation.
Well, so
but what is XZ?
If you have XZ, if this is the X direction, this is the Y direction, and this is the Z direction, then that square is parallel to the XZ plane. Okay, so XZ defines which plane in this case, which orientation we're looking at.
Oh, I see. When you give A, I see.
By the
Okay.
center.
Okay, good.
Yes.
I see. A tells you the center, and
Yes.
at that center you have 3 2-planes.
Quite so. So that's here.
XZ,
Yes, so
YZ,
that center we have.
and X. Okay, I see.
Exactly. So that's, yes. And
Okay.
similarly here, this would just be the points, and this would be the 3
Oh, you have the
directions for one cells. And here we have a cube, which is X, Y, Z again, if everything at some particular A. Okay, so now with the geometry we have here, well, as you see, for a particular A, particular center, we have 8 possible cells. And the geometry here is just that of the exterior algebra of R3. In other words, at a point, you can you have an exterior algebra acting, and you can take wedge products. So a general element of C, these chains, is a linear combination of the cells by some scalars. So it's given by these map these functions fi. So fi here is a function of a. In other words, it's a function of a lattice point, whatever you want your coefficient system to be. So now you,
Well,
in order to specify,
so f sub I is like dx dy, sort of.
yes. So here you need to choose 8 functions, 8 scalar valued functions on the lattice, and that will specify an element of the chain space.
Well,
Okay,
well,
because
in all the possible degrees.
yes, so that, yes, if we're in 3 dimensions, that is, yes. So what operations do we have here? Well, we have wedge multiplication, in other words, which is pointwise defined. So if you take 2 chains and they're not based at the same point, they don't have the same center, then the result will be 0. If they are at the same center, then you just take the wedge. The type will be of the wedge in the sense of this exterior algebra action here. And then we have boundary in the usual sense, that if you had a cell, then the boundary will be the sum with the appropriate orientation signs of the cells on the boundary. So this is a degree -1 operation, so the boundary operation, square 0, of course. And if you want, you can also talk about the star operator, which is important if you want to actually write down equations or discretizations of equations. But as far as the algebra structure goes, all we have is the multiplication and the d. So that was chains. Cochains, well, it's actually the dual. So cochains will be defining functions on elemental cells. So a typical element in the cochain space will be given like so. So here we're just using the same notation of differential forms, di, to indicate on which type of cell we have this function fi. So again, you have exactly the same data to specify an element of the cochain space as an element of the chain space. Simply, we write it differently. Here, this refers to a hypercube, and this refers to a cochain element. And the operation again, well, we have again same type of operation, which is multiplying the coefficients pointwise. But now we have coboundary, which has degree +1. So although it seems that the spaces are essentially the same, we've used slightly different notation, but the data is exactly the same. The fact that one has degree -1 and the other has degree +1 means that the multiplication and the d operator will interact in very different ways in the 2 settings. Yeah, as we mentioned before, we have some adjoint property, and the star also the usual identities between star and del, and which we won't go into here. Okay, so here I mentioned what we just said, that we have the same linear structure because the lattice is self-dual, but very different interaction of the multiplication and the differential in the 2 cases, the cases of chains and cochains. So just so we're all on the same frequency, let's look at the 1-dimensional case. So in 1-dimensional case, you essentially have a bicolored 1-dimensional chain, again, 2n elements. This is our lattice. You have 0 cochains and 1 cochains, and on the other side, 0 chains and 1 chain. So the 0 chains are the points, which in our notation, well, it's just empty set wherever the point is, point A. So that's, sorry, that is a point. The 1 chains are intervals of length 2h with center A. So in other words, this will be A minus H, A plus H. 0 cochains will be functions, and 1 cochains will write f of x dx. Okay, so what's the boundary operator? We take a general cochain, so that will may have a 0 component and a 1 component. Then what is the coboundary? Well, coboundary has degree +1, so the 1 cochain part vanishes, and we're just left with the co-boundary of f of x, which will be f of x plus h minus f of x minus h dx. So that's the boundary, the co-boundary operator. The boundary, on the other hand, when we're dealing with chains, well, points don't have boundaries, zero boundary. So we'll be left with just the boundary of the edges. The boundary of an edge from a minus h to a plus h will be at a plus h minus a minus h. So in other words, we just have a combination of points like so. Okay, so that's all very simple. Yeah, with the continuum derivative, notice that we just have differences here. So we want something like the continuum derivative. We want a divided difference. So we'll have to divide by 2h. So these are the objects that ought to be comparable with a continuum derivative. Okay, so on both sides, we have commutative structure. We have a multiplication, which is commutative and associative, but doesn't satisfy Leibniz. So remember, we wrote down at the beginning what happens if you take a divided difference. Well, now we have symmetric divided differences, so slightly different. So the appropriate formula here would be this. So this is the symmetric divided difference of the product. This is what it ought to be if the sum of the first two terms, if Leibniz was satisfied, and the error is what we've written here. So now the error is in fact the sum of two terms, and you can write it in this form. So the error from being Leibniz, this difference here becomes this sum, where now each term here is a product of half divided differences. So we have delta is the forward divided difference and delta prime is the backward divided difference. So x plus h. And this is the backward one, f of x and f of x minus h over h. And this is the error from Leibniz. Okay, so yes, as Dennis said, if you want to write Navier-Stokes, for example, then you have terms of div, grad, curl, Laplacian, and so you need d star and star operator. So I just wrote down Dennis's models, two models of discretization of Navier-Stokes. So we haven't, there's one more operation needed here, which I wrote at the bottom here, but I'm not going to go into some operation which goes from vector valued 0 cochains to scalar valued 1 cochains. But the important feature is, of course, it's not linear. And so we have a multiplication here or here. And so what we want to do is to study this error from being Leibniz in a quantitative way. Okay, so very general algebraic theory, so you start with a graded vector space with a multiplication, which is commutative and associative, and a differential, which has degree plus or minus 1, square 0, but not obeying Leibniz. So we want to analyze the structure here. And by that, we mean what we're going to do is to construct an infinite sequence of high infinitesimal cumulants. So the first, these are going to be maps from the symmetric powers of A to A. The first D1 is just D. D2 is the error from being Leibniz, so that you can think of as the bracket of D and M. You think of these as operators A to A and A cross A to A. Yes, if you look at this expression, when you interchange A and B, then these two terms interchange. So you've multiplied by this sign, this term also has changed by this sign. So in other words, this is not just a function of the pair A and B, but rather you can think of it as a function of A wedge B. So this is really a map from S to A as advertised. Okay, so that's.
Is it worth saying what you mean by S of A is when A is graded vector space? Just to remind everybody.
Yes, actually I've got that on the next page, but yes. So in other words, you think of it as a, well, okay, yes. So you consider S of A, so you think of it as a subset of subspace of the tensor algebra. And so this would be a sum over all permutations with the appropriate sign. And the sign here depends on the grading of V1 to Vk. Okay, so this is this error from satisfying Leibniz.
Can I quibble?
Yes.
That's not a subalgebra. I mean, it's a sub-coalgebra. So you usually take the quotient by identifying AB to BA with the sign, right?
Okay. Yes.
Because you're going to talk about coalgebras in a minute.
Yes. Okay.
But I mean, intuitively, the vector space is a direct sum of all these things, but it's the even elements plus the odd elements. And S of A means the polynomial algebra on the even elements, tensor the exterior algebra on the odd elements. I mean, that's
true.
Yeah.
Yes. Okay, thank you. So in this sequence, starting with D1 and D2, so now we also have D3. So I've written down some expression here. It's a sum of 7 terms now. So we have all sorts of signs coming in. As you can see, we're taking D of some product of some subset multiplied by the remaining terms. And so we have various sorts of signs here. Altogether, there's this concept of a causal sign. If you interchange two symbols, if you have some symbols which have weightings and you interchange two symbols, that introduces a sign which is -1 to the product of the gradings of the symbols. So here I want to take D to be graded odd and the other algebra elements to have their usual grading. So then, for example, if you look here, then the order we want is D, A, B, C. So the difference here is that C and B have to be interchanged, and that corresponds to what we see here. And here, for example, D, B, C, A. So now we've interchanged both the order of A and C and the order of A and B. And so we have A times B and also A times C. So that explains those signs. And the other signs, these major signs, we're taking D of the product of all 3 elements and then minus D of a product of 2 elements times 1 outside, and then with a plus D of 1 times 2. And then again, a minus, well, sorry, that's the last term, in fact, yes. Okay, so there is a way of some combinatorial combination. The way I've defined it so far doesn't really explain where it comes from, and I'll give you a better definition in a moment. But one thing to note here is that there is an iterative procedure. So D2 came from D1 by taking a bracket with M. So now you can think of similarly D3 as coming from D2, again by taking a bracket with N. If we fix the last term, the C, so if we ignore the C, think of it as some fixed object, then we have D3 of a pair is given by T2 of the product minus, this is just a causal sign, times here A times D2 of 1 and minus B times D2 of the other. So it's exactly the same format as we had over here. And so that means that in fact we have a recursive
just a minute,
here.
Naively, D2 has 3 terms, so you should have 9 terms here, but you said you only had 7 terms for D3.
Yes, so you really have to fix C. So you can't take all combinations. You have to think of C as fixed. Now you could say that that sounds very asymmetric, and indeed it does sound asymmetric, but the expression you obtain is symmetric.
Oh.
Yes, so it's important what I've drawn down here at the bottom that you take, say here, dk minus 1, it has k minus 1 inputs. You fix all but 1. So you fix k minus 2 of the inputs. Now you're just thinking of it as a map with 1 input and 1 output. Of course, it had actually k minus 1 inputs, but we fixed all the rest. Okay. Now, if we take that map with 1 input and 1 output and take its commutator with multiplication, then we get something with 2 inputs and 1 output. 2 inputs and 1 output. But of course, all along, these other k minus 2 inputs were fixed. So that is actually dk. Okay, so as I said, this seems to be a rather asymmetric way of defining it, but actually the result is completely symmetric. We have that's a recursive definition. And now that we're here, let's just mention that when D2 is 0, So D2 being 0 meant that this expression vanished. So that gives you Leibniz. And then you have a differential graded algebra. Whereas when D3 is 0, so now we have the sum of 7 terms is 0. So that's a weakening of Leibniz. Leibniz doesn't hold, but you have a 7-term relation, and that's called a BV algebra. And you also notice from here that if D2 was 0, then so would be D3 and all subsequent ones. And similarly, at any stage, if one vanishes, then all subsequent ones will also vanish because of recursion. Okay, so that's
So this is
some general
a
theory
big,
and how
a big
fit it together.
tautology, right? This is a
Yes.
big tautology.
What's going to be on this page? Yes. So in order to fit this together into a nice structure and to be able to see some functoriality out of it, let me just give you a little bit of algebra. So if we start with A, then any algebra A, any vector space A, you can consider S star of A. So that you said you don't want to define it this way. Okay. And it has a coalgebra structure, which is given as I wrote here. So you take all splittings of a wedge into one side and the other side. So for example, if you had a wedge of 3, then you split them into 1 and 2 in all possible ways, or 2 and 1 in all possible ways, and then the signs of the causal signs, as we explained earlier. So as usual, whenever you have an algebra, an algebra, if you want it to be associative, you can write its property, and to produce the dual version on the co-object, reverse all errors. So saying that the co-multiplication is co-associative is just this statement. This diagram commutes. And indeed, having written down the co-multiplication, I mean it's a co-multiplication which is co-commutative in the graded sense and co-associative. So S star A has a co-algebra structure. As you say, this is tautologous. We're not using anything at all except not using any structure on A at all, except its linear structure. Okay, now on an algebra with multiplication, a derivation is something which satisfies the Leibniz property. So that you could write in a way, composing the maps D and M. And by this idea of reversing arrows to produce the co-object, similarly, a co-derivation will be anything that satisfies precisely delta composed with D is the composed identity plus tensor the identity composed. Yes. So here, by the way, again we have a sign because we've written DAB, and here we've changed the order. So this sign appears, and when you write it in this form, this identity with a bar is just taking into account that sign. So that's exactly the same operator here. Okay. By definition, again, any algebra map from A to S star A, this is thinking of it as the algebra S star A rather than the co-algebra, can be extended to an algebra map from S star A to S star A. How? Well, if you have a composed object, then you just simply multiply the images of, so if you have a map defined on A, then how do you define it on S2A or S3A? Well, you just take the appropriate wedges. So similarly, when you change the arrows around, any map from S star A to A can be extended to a co-algebra map, which will be from S star A to S star A. And the infinitesimal version of what we just said is that on the algebra side, any map from A to S star A can be extended to a derivation. How would you work out the derivation on a wedge? You just derive each piece using alpha. And that will now be a derivation of S star A. And so the dual version of that, the co-version of that, will be that any map from S star A to A can be extended to a co-derivation from A to S star A. Okay, so this is all tautologous algebra, which now enables us to fit the higher infinitesimal cumulants into some sort of interesting picture. So what do we got? We're starting with the algebra, which is commutative and associative, and a D, which has D squared equal to 0, but it does not satisfy Leibniz. Okay, so, and we've just seen that S star A has a natural coalgebra structure. Given the multiplication on A, well, we have a natural map from S star of A to A, which is take an elemental wedge and take its product. So that's using the multiplication now. Now, as we just said, any map from S star A to A can be extended uniquely to a coalgebra map. So we do that. And what you get is what's called the cumulant bijection. So it's not entirely trivial. The base piece of it, the piece that just involves A, is just the multiplication. That's this thing here. And then you have other pieces and signs and so forth. So this is something that Dennis worked on with Nissim. And this is a very clever object. So this is, as it says, it's a bijection. It's a coalgebra map. By definition, that's what we've done.
Can I say something?
Yes.
I mean, this tautology you've been discussing was sort of discovered by physicists, and this is sort of a formulation of it in math terms, you might say. And this was, cumulant bijection was motivated by an Einstein chair lecture, and it's on tape. You can read it, and it's in this series, but it was like November 2012 by Jason Park, who was doing he just started writing formulas and was doing something which was tautologous and getting into some kind of algebra close to the BV formalism that he was trying to explain in quantum theory. And it was just, your beautiful discussion here is that it's just explaining, a tautologous way a mathematician can arrive at it, you might say. Okay. It's a formulation. Yeah.
Yes.
Well,
Okay,
Jason
so-
Park. Did you write his name there? Jason Park?
Yes. Yes.
One can hear how he talks about it. And then there's a paper he wrote in Archive in 2018, right?
Yes. Okay.
Archive
I think
2018.
yes.
Yeah.
Yes. Okay, so we now use the product map. We use the product on A, and we've somehow encapsulated that in this coalgebra map, this tau. On the other hand, we have a map from A to A, and that can be extended to a co-derivation. So you can also think of it as a map from S star A to A, where everything except the first piece goes to 0. And that can be extended to a co-derivation. And this is the formula for it. So you're just acting on each piece individually. I've moved the D to the front. That will just pick up some more signs, meaning omit the ith term. Okay, so now we make a definition.
So
Capital
it's also
D,
a derivation, right?
it's also a derivation, yes. And it also has square 0.
Yeah.
Because D squared was 0, yes. So now we make a definition. We have D hat is this map from S star A to S star A, which is a co-derivation. Tau is a coalgebra map, and we conjugate D hat by tau, and that will then still be a co-derivation. So we have a map from S star A to S star A, which is a co-derivation. Just a conjugate of the original co-derivation. Because D squared was 0, so D hat squared is 0, and so this big D squared is 0. It's a conjugate of something whose square is 0. Now, a co-derivation, just saying again what we said on the previous page, but the other way up, a co-derivation is determined by its first component. And the first component is determined by its pieces. So for each K, we need to specify where this maps to. These are what you can call Taylor components. The Taylor components of D are D1, D2, D1, D2, D3, wrote on this page here.
So that's
So
a
these
theorem, right? No,
That is a theorem.
Yeah.
Yes. So yes,
They're
sure.
calculation. Yeah.
Yes. So these D's, well, maybe I'll write it here. Yeah, so these D's are, well, they're maps, as we said, from SKA to A. They can be called K brackets because they have inputs which are K tuples of elements of A, or you can call them, you can call it the K minus 1th higher infinitesimal cumulant. Because if you like, D1 isn't anything, D2 is the first infinitesimal cumulant, it's the bracket of D with M. And then the higher ones, second one is D3, and so forth. We have this shift of one in the notation. Okay, so what does that mean? The Taylor components are D1, D2, D3, as we just said. For each D, for each map, we can define, we can extend it to a co-derivation. For each map from S star A to A, we can extend it to a co-derivation. So if we extend each of the individual pieces, then co-derivation, which when you add them all up, will give you the big D. So, sorry, you can think of this. So this D1 hat, well, D1 was D. So this is just D. D2 hat, well, that came from the bracket. That was the bracket was the commutator of D and M. It was an error in Leibniz. Whenever you have an A and a B, you have the error of D, of the product of AB, from being essentially dA wedge B plus with a sign A wedge dB. And then, well, of course, this squared is 0. This plus this doesn't have square 0. And now you're fighting to get back to something which does have square 0, this D. So you can keep adding terms which are correcting the fact that this square was not 0. Now you add this and you keep adding these terms. And in the end, D will have square 0. So that you can think of as an infinite family of properties. So for example, you could say, of course, D1 squared is 0. D1 commutes with D2. D1, D3. This is an odd operator, so we can break a bracket itself, and so on. So we have an infinite sequence of such things. And okay, so in the philosophy of infinity algebras, you can think of doing this operation, and that will get you to the big D. So now we see that all these different K brackets have fitted together into a single operator D, which is a co-derivation of square 0 on S star A. So I've just repeated that here, and then I've written down what the format of these different pieces of the co-derivation are. So here it was just D hat. So in other words, it was D acting on one piece. Here we had D2 hat. Well, that really is extracting any pair and taking the 2 bracket is D2. And here we're taking triples and so forth. So these are higher and higher, what's called Grothendieck order operators. Derivation. Okay, and now the definition, which we just had, you can write this commuting square. So we're saying that the D is given by conjugating D hat by this magic object, the cumulant bijection tau. Okay, so now this is theory, what you could call, as Dennis said, you do have to prove that the formulae all match together nicely. And you can do that starting from any algebra, commutative associative algebra with a D which is square 0, not satisfying Leibniz. So now you can actually take our bicolored lattice model, the thing we described before. You can take cochains with a wedge, with the co-boundary. Well, I've normalized it because we want in the end this to somehow approximate the continuum model. So we take this particular input. So this is our A, this is our multiplication, and this is our D. And out of it, we get the family of DKs, the brackets, the higher infinitesimal cumulants. And the question is, what do you get? Well, so the theorem here is that DK can be written, so DK is now supposed to be a map from SKA to A. So it has input a K tuple of cochains, and the output will be a single cochain. And the result is that you can write a formula for it, which extracts this power h to the k minus 1 times a sum of products of divided differences. So these are precisely the delta and delta bar that I wrote down at the beginning. Now we have them in the one-dimensional model. So now we have them in all 3 dimensions if you're in 3 dimensions, and theorem works arbitrary dimensions. So this is the analog of what we did in 1 dimension for D2. So we had this formula right at the beginning. You remember here, we had this formula, the difference between, so this difference here, term we have here, this is D2. This is D2 of Fg expressed as h to the power 1 times a sum of products of divided differences. So this theorem is saying that that works in general, arbitrary dimension, arbitrary order. Sorry. Okay, now, on the other hand, if you start with chains, and this will be space, this will be multiplication, and now the D operator will be the boundary, then you get a different power coming out. So you get twice as many terms here, it turns out, and you get h to the k minus 2, as long as k is greater than or equal to 2. So just to give a little bit of an intuition on this, what happens when h goes to 0? You expect somehow that the discrete calculus that we have here will converge to the smooth version. So what happens when when h goes to 0? So well, D1 is just the base. D1 is delta over 2h, and this goes to the derivative in the usual sense. D2, well, we've now said that D2 is divisible by h, so that goes to 0. So that was the error from Leibniz. In other words, the error has disappeared, and we've now ended up with a differential graded algebra, namely the differential graded algebra of differential forms. So intuitively, that makes sense. Whereas when you look at chains with boundary, well, again, you believe that this is going to go to the continuum derivative. Now, when you look at D2, well, there's no factor of h here, so D2 remains non-zero. D3, however, is divisible by h, and so goes to 0. So D2 is giving you a bracket. In other words, it's saying that the non-trivial bracket, what is this? Well, this is the algebra of polyvector fields. The bracket here is the Schouten-Neuhaus bracket on polyvector fields. And the fact that D3 has gone to 0 is saying that this is really a BV algebra.
And this fancy name you said is just the extension of the usual Lie bracket of vector fields, right?
Yes, yes, quite so. So now that's fine when h goes to 0, but of course we don't actually want to just look at h goes to 0. The whole point of this analysis is that we have a quantitative setup which gives exactly what the decays are in the general setting, not just they go to 0 in certain orders. Now, what happens when you compare different scales? So let's suppose that we have our cube subdivided into, well, here we had the 2n by 2n by 2n lattice with size h, and then we go to a coarser lattice with size 2h, n by n by n. So we now have a coarse lattice sitting inside the fine lattice, and any chain in the coarse lattice can be subdivided into cells in the fine lattice. So you have a map from the chains in the coarse lattice to chains in the fine lattice. Similarly, in the other direction, cochains on the fine lattice will map to cochains in the coarse lattice, and that's by some sort of integration or averaging, depending on exactly how the normalization works out. So in other words, have a cochain on the fine lattice, you have to define a cochain on the coarse lattice. Its evaluation on a coarse chain will be given by summing over all the subcells, fine cells inside that coarse chain, the value of the cochain on those elements. So we have some sort of a subdivision. And you take the values and you average them or you sum them, whichever seems appropriate. So these maps are chain maps. In other words, they commute with the appropriate D. The crumbling map commutes with the boundary and the integration map commutes with the co-boundary. But they do not respect multiplication, of course. So we want now to somehow compare the D, the capital
Well,
D that's been.
Well, wait,
yes?
wait, the mantra is the average of the product is not the product of the averages, right?
Yes.
I mean, it's like an average, so
Yes.
that's because of statistics, right? I mean, and the
Yes.
cumulatives, right?
Yes. So now the question is, how does this affect D? So we have a D on one side of the picture. Here we have a D, here we have a D bar, and we'd like to somehow quantitatively relate the D and the D bar. Or equivalently, the whole family of the decays and the decay bars, but obviously it's going to be easier to relate them algebraically when you put them together in the most functorial form. Okay, so this is where the capital D comes into its own. We have a averaging map, this bar, which is going from, we're looking at cochains now, going from cochains, fine cochains to coarse cochains. And we have, well, on each side of the picture, we have D as given by this, so D is a conjugate of, in this case, delta, because we're dealing with cochain, so we have a co-boundary. So that means that we have here our D, and we have here our D bar. Now, the two sides of the picture are related because we have the averaging map. So the averaging map gives, functorially, you simply have a map from S star A to S star A bar. And that will also be here. We just said that the integration map is a chain map. In other words, it commutes with delta. And therefore, this commutes with that. So this is the square that we have up here. Okay, so now you have, if you take the composition here, it's exactly the same. Oh, sorry, I didn't.
I mean, the upper square is, excuse me, the map from A to A bar commutes with delta, right?
Yes, this
And then
commutes
that's
with
what
delta.
you just said, and you just applied the functor S to that commutative
Indeed.
diagram. Okay.
Exactly, yes. So now we have a commutative square on the top. Now we can look at the composition here. So this gives a map. I should do it in a different color. This gives a map here, which we'll call sigma. We have exactly the same map going on here. So here we have a map sigma, which is an intertwining map from S star A to S star A bar, which is given by this composition of tau, S star of bar, and tau inverse, tau bar inverse.
So you define sigma to make the diagram commute, right?
That's right. And now you look at the bottom part of the diagram, this bottom square, which now, because everything else commutes, this must also commute. And what's this telling you? This is telling you that D and D bar are related by this intertwining map sigma. Okay, so that sigma intertwines between D and D bar. So what is this sigma? Well, sigma is a map. It was this composition here. It's a composition of coalgebra maps. So it's also a coalgebra map. It's a coalgebra map from S star A to S star A bar. And the coalgebra map is determined by the first piece. In other words, a map from S star A to A bar. And that has its Taylor components from SKA to A bar. What are they? Well, the first one is just averaging. The second one is this cumulant. This is the extent to which the bar was not compatible with multiplication.
So excuse
And
me,
then-
in fluid mechanics, this is the term that they call the Reynolds stress sometimes. Right, because, okay, in some context, yeah.
And then if you can simply write down higher terms, so you get some combinatorial terms here. And these are in fact well-known formulae. These are what are known as commutative cumulants. So these are commutative cumulants of bar with respect to the two multiplications on the two sides. So we have the multiplication on one side, on the A side, and then we've taken the bar of that. Here we've taken the multiplication on the A side, but it's now in A bar. This is also in A bar, and the multiplication here is in A bar. So both multiplications are involved in this formula. And okay, so that's the formula. And this gives you the relation between D and D bar. So again, we can ask what happens in our particular case. And the answer is that, well, if you take the case of cochains, so then you're taking fine cochains, the coarse cochains, exactly the diagram I was writing just now, you're integrating, averaging. Then there are normalization map you get is such that, again, you have this h to the k minus 1 divisibility. So what that means is that, so I didn't actually write the formulation. You want me to give the formulation in J-Suk-Park's terms? So J-Suk-Park defined a, what he called this was a binary QFT algebra. So he had some notion of a binary QFT algebra. And our divisibility properties, if you essentially satisfy his axioms. And so what they mean is that starting from the cochains and delta, then this will give you a binary QFT algebra, and the renormalization map is a map of, so it preserves that structure, it preserves the divisibility properties, is a map of binary QFT algebras. And similarly for the chains with its boundary, except that we had a shift in powers of H. So in order for it to satisfy the axioms that he wrote, then we have to not divide this by H. And then similarly, we'll have a normalization map here. So what we will end up with, if we take a system of finer and finer lattices, is a whole string of different structures and with maps in between them. And those are supposed to contain the information of the discrete information of the errors of the multiplication from the D from satisfying the Leibniz property with respect to multiplication. So Dennis, I wrote on the bottom here that little what I said today, but maybe there's no real need to include it. So this was the final story, that we have a family of difference calculus approximations with their renormalization maps, which approximate to the continuum vector calculus. And these approximations, we mentioned when H goes to 0, if you ignore all the powers of H, then you get to the continuum picture. If you include the powers of H, then you have a quantitative formulation of the errors and errors on errors, so to speak. And the hope is to be able to use this quantitative calculus to be able to add higher order terms to a discretization of some system, if you want to discretize a model, in order to mimic at a coarser level the behavior of the system. So the aim is to recover the memory of renormalization, which is Falkovich's phrase, what we really want to do when out of discretizing a model in a useful way. Okay.
I can see that you're a good teacher, Ruth.
Thank you. Are there any questions?
Thank you very much, Ruth. Yeah, that was a very beautiful
Thank you.
talk. Yes, and I'd like to open the floor to questions for Ruth. So I have one. Can you make any comments about the regularity of those functions you were saying you mentioned earlier that were defining the chains? Are they just C infinity?
They're completely
those functions?
discretized. Yes.
Oh, they're completely
so, I
right.
mean,
Right. Okay.
yes. So everything's finite here. That's yes. So I mean, what was written at the bottom of this previous page. So the question: how can you say that something is of order h to the power n if h is actually a finite quantity? So one way of doing it is like this. If you think of it as take a unit cube, and then you're subdividing it by in powers of 2, then if you fix a trigonometric polynomial function of x, y, and z, then you can those can be defining the coefficients in your cochain. If you take such a function, then you can restrict it to lattice points. And then that gives you a cochain. Then you can take k-tuple of cochains, and then you can take the evaluation of the delta k on this. This will give you an output, which is again a cochain. The cochain is given by coefficients, which are functions of the lattice point. You can then take the L infinity norm of that, and that will be of order h to the k minus 1, or h to the k minus 2, depending on whether you're using delta or del. So, and you can actually write down an explicit bound in terms of the size of these coefficients here. So that's a way of somehow connecting with the continuous model. Of course, this is absolutely smooth. So only in this case, when you're using trigonometric polynomials, can you write something down of that sort. But of course, the idea is to, if everything is discrete, then that allows approximation to whatever you want.
So I suppose if this was on a different domain, like a bounded domain R3, then the analog of the trigonometric polynomial would be some different basis from the Laplacian, for example, on that domain. That would be
Yes.
an analog of. Oh, yeah. Okay.
Yes, it seems so. Yes. That seems right. Okay. Well, obviously, there's a lot of work to do to turn this into something which will actually be practically applicable to an actual PDE, but it's a start.
Well, or PDEs are often considered to be models of physical processes, and then you could ask different questions, not about using this. You could try to use this to study the theory of the PDE, but you could also use it to try to study observables of the physical process that are somehow adapted to the algebra that is evolving here. I mean, it's a slightly different point of view. They're roughly the same mode, the same kind of inspired by the same idea. You want to study the PDE, or you want to study the physical process the PDE is supposedly modeling, but you can look at it in 2 ways, you might say. Yeah. See, this algebra has a certain structure, so it leads you to certain things that you might not think of with the PDE, because here we're studying how one of the algebraic rules in PDE land breaks down, right? In PDE land, you have all these rules, and one of them is breaking down here. So, and it seems to only break down in a certain power series compatible way. So, yeah. Oh, you might mention Theo's observation about integration by parts. I think PD
Yes.
people that under.
Well, I
Theo,
think
do you
everybody
want to
here
say
probably
what
knows
it
that.
is? Can you formulate it? I mean, one of the main applications of the Leibniz rule is the integration by parts trick, right? Which is very important. So,
Yeah.
so
So
you
in the
observed something.
periodics. Yeah. I mean, it was a while ago. I mean, in the periodic case, the integration by parts for these operators, that identity holds if you sum over the entire lattice.
Because the shift, intuitively the shift goes
Yes.
away when you're averaging,
Yes.
right?
Yeah, because the
With
spaces
integrate.
somehow shift invariant, so can relabel.
Okay,
Yeah.
right.
It's very
Leibniz
interesting.
is sort of violated locally, but not globally in some sense,
Mhm.
because you can integrate by parts. So that's.
Would this framework be able to capture when that fails, when one can integrate by parts or not? Because I know that, I mean, that's the issue in energy conservation for Euler. Above a certain regularity threshold, integration by parts is allowed. Below, it's not, and so above this regularity threshold, energy is conserved.
Well, it has to be stated carefully, because in those two models that Ruth mentioned at the beginning, you know, the Leray model with the derivative outside, and then the model inside. And if there's no viscosity term, you can prove energy is preserved in the model with the derivative inside. And you can't prove it's conserved outside, because if you could, it would, I mean, and this shows up numerically, that one model seems to behave with nice initial data, seems to not blow up, and the other one is very numerically unstable. So I don't think you could prove the energy in one conservation in one model, and you can literally prove it at the finite level for the other model with the D inside.
Mm-hmm.
And, you know, that kind of fits with the idea that in the theory of weak solutions of the equation with the D on the outside, there's been all this very interesting recent activity proving all kinds of things about the flexibility of those solutions, right? So it sort of fits philosophically. Because those weak solutions can't be defined for the model with the D on the inside. I mean, at the PDE level. So D on the outside, they can be defined. And then on the computer, they're kind of, the computer computations are kind of wild in that model. Whereas in the other model, they're not so wild. So it kind of fits. Alexander Sneelman, do you have any comment about these weak solutions? Because you made some examples, right? In dimension 2, right? Or something, but.
I think he did, yeah.
Huh? He's not there?
I think maybe the connection's bad, but yeah, he did.
His picture's there. His picture can answer for it. Ruth, I feel so ashamed after watching you give that talk. My talks are so bad compared to that.
No,
talk.
no.
I could never give that talk. It's fantastic.
Simply, thank you very much. Simply, I wrote out a summary beforehand, but actually Theo has a very good technique, which I tried to emulate.
It's really nice. Yeah, I think I understand a bit better now. I mean, it would be really interesting if you could show that by, numerically say that you could make models on coarse grids, compare them to models on fine grids, and improve the comparison by keeping more of these terms that you're developing here.
Right.
Um,
But
Yes.
But in some sense, you can't do that, right? But it could be that relative to certain considerations, you can do it.
yeah,
That's what the memory of renormalization means, that
Yeah.
phrase of Falkovitz, right? It's sort of a tautology. There are some things for which that will work.
Right.
But we don't know what they are, and there's some things for which probably can't work. I mean, it's
Obviously, you've lost information. So the question is, what information is still there when you move out
Yeah.
the course of scales? Yes. Apparently, there is something that you see on a larger scale, as you often say. You look at a river, or you look at water flowing, and you see that there are clearly quantities that are conserved
right.
and make
There's
sense on a
see
global
nice
scale.
pattern. Right. Yeah, that's sort of
Yes.
why I worked on this. I remember
Yes.
40 years ago, living in Boulder, I walked every day to this department past the Boulder Creek. I looked at the creek growing over these rocks, and I could see all this structure. And if I went closer and was looking closer, it would be more complicated. But you can see this structure. So it's like there is structure, but what's the formula for it? Alexander, I was going to ask you a question. Are you there, Sasha? Schneerman, can you hear me?
Yes, I hear you.
Yeah. Well, we were talking about one of the models Ruth said with the derivative on the outside, which allows you to define weak solutions. When you put it on, when Daniel Ann put that model on a computer, even for very nice initial conditions, it was very unstable numerically. And the other model was very stable numerically. And then, of course, the model with the derivative on the outside allows you to define weak solutions for the PDE. And then there's been, what's his name? Scheffer made the first,
Scheffer.
huh?
You mean Scheffer?
Scheffer, yeah. And then didn't you make some examples too?
I don't know. No, I didn't.
Well, okay,
think in
well,
these terms. But the phenomenon you mentioned now looks like you take the heat equation, and when you take the time derivative is approximated by step forward, it is unstable. And if it's a step back, it is stable. Maybe it is similar.
So which one is stable and which one's unstable?
Step back is stable and step forward unstable.
Uh-huh.
You mean divide the difference u t plus h minus u of t divided by h, it is unstable, and u of t minus u of t minus h, it is stable.
Well, there's the symmetric difference. So wait a minute, there's three things: forward, backward, and symmetric. So
no, it is forward and backward. It's not symmetric. I think with symmetric, it will be also unstable.
no, but there are three differences, and you're
Yes,
only
yes.
talking about a distinction between two.
Yes, yes. Here we have two. About the third, I'm not sure.
No, but okay, there are three things, and you're making two comments, and I don't know. I've got 6 permutations of interpretations. Can you state it again?
Yeah, so we have a simple heat equation. Ut equals second derivative in x of u. Now you approximate second derivative by symmetric combination, and the time derivative
Oh,
you can use the step forward, and it is unstable. You can use step back, and it is stable.
oh,
But
okay.
yes, and I don't remember what if it is symmetric.
Okay, but isn't that related to the Ito integral and the other person's integral?
Oh,
That's there's a Russian
course.
name, 3 or 4 syllables starting with S or something.
Stratanovich.
Yeah?
It is
Stratanovich, yeah. Isn't that the
Stratanovich,
comment
yeah.
about that?
In fact, I don't know. I did not think about it, but maybe.
Because you're talking about the second derivative the second difference, right?
No, the first difference. No, it is.
I heard you say second derivative approximation.
No, a second derivative
this is-
in the x direction,
Yeah.
and first derivative in t direction.
Oh.
Yeah. So and the problem is with the t direction.
Yeah, sure. Right.
Yeah.
Right. So that's the parabolic story.
It looks like a small difference, but it changes qualitatively.
Right. No, right. Okay.
Interesting.
Yeah, but there's another point. I mean, assuming that you're doing the stable direction, you're studying analogs of Brownian motion and heat flow and stochastic differential equations, there's this other nuance, the Ito integral and the Stratanovich integral. And one of them satisfies calculus chain rule properties and the other one satisfies something else. Do either of you know, Vincent or Theo, about those things? It's like stochastic PDE 201 or something.
Right.
And then it does involve, I notice this all the time because when Ruth was talking about how you define the cup product between 0 cochains and 1 cochains, there's really 3 possibilities. The initial, you multiply by the initial thing or the second thing or the symmetric thing. And, the first 2 are associative and not commutative. And the third one is commutative and not associative. And they fit with the Stratanovich Ito thing, except you use, they fit somehow. I mean, all these discussions are kind of, there's a lot of discussion just to look at the interval and look at 3 points on it.
Mm-hmm.
And there are these big theories. I'm kind of a neophyte in all of them. So, does anyone? This is just cocktail party knowledge about, there's Ito's formula that is useful to prove some things, and then the Ito integral. And then there's this theory of rough paths, that Terry Lyon's name is associated to. And, these integrals fit with that theory of rough paths. It's very interesting. There's Young's lemma, Young's lemma from the 30s, right? If you want to integrate a smooth form over a fractal curve, then you have Holder continuity. And if the Holder constant is bigger than 1/2, then the obvious secant approximation works, you get a geometric series, right? That's Young's lemma. And then if you want to let the Holder thing vary between 1/3 and 1/2, then you have to give a quadratic, like a variation term.
Mhm.
And that's related to the Ito integral and Brownian motion, and Paul Levy and the Ito integral gives a formal construction of this information for a Brownian path. So a Brownian path has this second order information. So this and then when you, in theory of rough paths, then if you give that extra information, then you can, so to speak, go fill in the gap from 1/3 to 1/2, and then all the higher calculations can be made. And then if you want to go Holder from 1/3 to 1/4, you have to give a cubic piece of information, which I don't know how to do, and I don't know anything about that, but et cetera. And that whole fits with another formal expansion, which is called the lower central series of a free group. So anyway, all of these things are interpreted, and you can just stay on the real line and draw a few points and then talk about them. So
Yes.
I only have this cocktail party knowledge of these things, except one of them I understand more deeply because of algebraic topology. The whole lower central series discussion makes sense in algebra, so we know about that topology. But this is also a line here. Okay, someone's trying to say something?
Yes, two things. One question. Is it all this theory somehow related to the formula of change of variation if you
Yes.
in the derivatives? Yes. So if we consider higher derivatives, then we have a long tail. To this. We have one algebraically simple term, and the other terms are no, something like this. So the first term, the first order derivative is transformed in known way, in the usual way, and the higher order terms, there appears something, some other terms.
Yes.
Does this theory relate to the algebra of that remaining terms? But they
Well,
have some.
I would say it would be nice to fuse. It would be nice to fuse those things together. The one with the other term is called the Ito formula, right?
Yes, yes.
And
The second
the
term
Stratonovich one is the one without the term, right?
Yeah.
It would be nice to fuse that statistical idea with this pure algebra. That would be nice, yeah. Because then you would like to see this algebra might, I see how to begin to see how to try to use it for Euler's equation without the viscosity term. And then you can just formally throw in the viscosity term. But if you want to really throw it in, what it would be nice to do would be to throw in Brownian motion and the Constantine-Hier formulation of the Navier-Stokes equation as the vorticity pushes forward when you average it over the backward process. So you put in Brownian motion and you reformulate in those stochastic setting, the Navier-Stokes equation. That would be the right way to, and then you could try putting those things on the computer with this algebra. That would, but you'd have to fuse this little discussion of 2 or 3 or 4 points on the real line with statistics. But statistics is jumping out of the page here. The D is, these terms of D are the naive statistical cumulants when you exponentiate these quantities and ask if they're algebra automorphisms or algebra maps. Then they're not. They deviate because it's not a derivation. So when you exponent, the idea of a derivation is something when you exponentiate, it becomes an algebra map. That's what a derivation means. So these deviations from being a derivation are like, so to speak, infinitesimal versions of the deviation of the exponential from being an algebra map, which those are the cumulates. So that's why we call them infinitesimal cumulates. And then the maps between scales, as Ruth calculated, are just exactly the naive statistical cumulates. These are linear maps that don't preserve the algebra structure. So you get all the cumulates. So all this stuff, you start with not mentioning statistics or not trying to do Brownian motion or probability, and you start doing the algebra and all these cumulates jump out at you. So it'd be nice to fuse, before you even start discussing which PDE you want to discuss, apply to, you could add Brownian motion to the Euclidean space and put that in. You have all these formulas that Sasha was just referring to, changing variables. I mean, that's further calculus in a way. It's, the Ito calculus. In fact, that's the name, Ito calculus and Stratinovich calculus. That's the next step after vector calculus. So you could try doing that. So I think it could be related and should be related. It is not now related. But since everything is just living on the real, you see that Ruth's discussion when she was saying, well, how would you multiply cochains? Well, that's what Ito and Stratinovich were saying too. They were saying, what differences do I consider, and so on. My hope at the beginning of all this was just look. So I'm like coming from not having taken PDE 1. Okay, so I look at the heat equation and I say, oh, du dt is Laplacian u. Okay, so I take a function with compact support and I stick that in. And I say, well, I don't know the solution, but du dt, use the right-hand side is 0 outside a compact set. So when you start changing coordinate, you start evolving this thing, it's not going to change outside the compact set. It's because I haven't taken PDE 1, right? And on the other hand, in the 80s, I was writing papers about Kleinian groups and using Brownian motion, because Brownian motion, you take the second derivative, you approximate it discretely by that second difference, and then you get this random walk interpretation of what this is happening. And then that's a discrete thing, and it converges like gangbusters to the actual thing. But then you can start thinking about it geometrically in terms of random paths, and then you can understand it. You can write papers and prove theorems, answer questions, about Kleinian groups and stuff like that. I mean, so I was hoping that if you just very naively took differences and developed the algebra inexorably, don't just assume anything, that you would find some structure. So Ruth gave a beautiful exposition of how all these cumulates come out. And then she also calculated that they have the right divisibility properties algebraically. So it's just, what's next? I don't know, but you don't have to.
No, one thing going next, some time ago, I wrote a small piece where I consider the motion on a rugged surface, or
on a what surface?
No, a non-smooth surface.
Yeah, rough surface. Okay.
Yeah, rough surface. And there is some small formalism similar to Ito, so that we can lose the energy without explicit friction.
Oh.
Yes, and the rate of the energy loss is related to the quadratic variation of velocity. No, I can send you.
Okay, yeah.
Text.
Like
so it is directly related to this stuff like on Zager.
Ah.
Yes. so it can go far.
So can you put that on the chat so it'll be in the recording? We're still recording, right?
We are.
Yes,
Yeah,
I
can
see
you
it
put
in
that on the
report.
chat? Sasha? That
Excuse me?
reference? Okay,
No, it has no reference. It is still
okay,
a
okay.
manuscript. Yeah.
Okay, well, you send it to me and, or send it to Vincent and I'll, or me, and we
I send you.
get it. Okay. Well, I'll try to
Yes.
get something ready for a couple of weeks. Okay, Vincent? And
Yeah,
then,
that sounds great.
and then if, but next week is open, right?
That's correct. Next week is open.
Yeah,
I'm going to stop the recording now.
okay.